Hey everybody. Today we're talking about the limit definition of the derivative, viewing the derivative as a function. Remember, the derivative of a function at a point x equals a is just the instantaneous rate of change of the function at that point. We take the change of the function over a small interval starting at the value x equals a, divide by the width of the interval, call it h, and then let that interval get smaller and smaller. If that limit exists as h goes to 0, then we call the value we get the instantaneous rate of change at that point, the derivative at that point. Now, we can do this computation for many different values x equals a. So really what we're doing here is defining a new function. Let's change notation to respect that fact. F prime of x is the limit as h goes to 0, f of x plus h minus f of x over h. The name derivative comes from the fact that we really are getting a function that's derived from the original function f of x. It's related to it, but not exactly the same. The domain of f prime is going to be all the x values for which this limit exists. Right away, we see that f prime can only be defined where f is defined. But it's perfectly possible that there will be values for which f is defined for which f prime is not, simply because that limit might fail to exist for some x values. We can compute using the limit definition of the derivative in much the same way as we compute the instantaneous rate of change of a function at a point. For instance, let's compute the derivative of f of x equals 2x squared minus 6x plus 4 using that limit definition. So the first thing we're going to need to do is to take this function f and plug in x plus h wherever we see x. Then we subtract off f of x and divide by h. Now, plugging in h equals 0 won't do me any good here. There's an h in the denominator, and I can't use limit laws when a denominator is going to be 0. So I need to do some simplification first and hopefully cancel out that h. I'm going to FOIL out in the numerator. X plus h is x squared plus 2xh plus h squared. And distribute the negative 6 and then that negative sign on that last bracket. Distribute the 2 and then combine like terms to get to a place where every term in my numerator has an h. Then I factor out that h and cancel, and I'm left with the limit as h goes to 0, 4x plus 2h minus 6. Now I am in a place where I can use my limit laws and plug in h equals 0. Overall, I get f prime of x is 4x minus 6. Notice in this case, the derivative f prime is just the equation of a straight line. Let's see how this looks visually. Here we are in GeoGebra. I've graphed the function 2x squared minus 6x plus 4. At some point on this graph here, using a red dot, I can draw a tangent line to the graph. So at x equals 1.5 right now, we can see that tangent line. The derivative of the function at that point is going to be the slope of the tangent line. At x equals 1.5, the slope is going to be 0. So the blue dot is representing the derivative at x equals 1.5. I'm plotting the point 1.5 comma f prime, which is 0. Now, as I move this red dot around, I'm going to be changing the slope of that tangent line and therefore changing the value of the derivative. So the height of that blue dot is going to change. For example, when x is 2, the slope of this tangent line is going to be 2, and therefore the derivative function is going to pass through the point 2 comma 2. As I continue to move this dot to the right, the derivative gets larger as the slope of the tangent line increases. And if I go to the left, it gets smaller as the slope of the tangent line decreases and then becomes negative. Overall, that blue dot is tracing out the graph of the line y equals 4x minus 6. That's the derivative function. There are many different notations for the derivative. Unfortunately, y equals f prime of x is not universal, nor is it the most useful in every situation. So you really do have to know several different notations for the derivative. In addition to y equals f prime of x, you'll frequently see dy dx. This has the advantage of explicitly saying what the independent and dependent variables are. Sometimes you'll see d over dx, f of x. Sometimes we say d by dx, f of x. Here you think of the d by dx as like a verb, telling you to differentiate the function f of x. When you get into Calc 3, you'll sometimes see capital D sub x of f of x. These all mean the same thing, and you really are going to need to know them all eventually. We can find instantaneous rates of change in a new way now. We can just take the derivative function and then plug in a particular value that we're interested in. Let's see an example. The position of a particle at time t is given by the equation x of t equals 1 over t for t between 1 and 4. So now t is going to be our independent variable and x is going to be our dependent variable. So we can look at x as a function of t. We want to find a function representing the instantaneous velocity of the particle at any time in that interval, and then use it to evaluate the particle's velocity at time t equals 2. So basically, we need the derivative function, and then we have to plug in t equals 2. Let's go ahead and use this new notation that we mentioned in the last slide. The derivative of the function x of t can be written dx dt. We need to do the limit as h goes to 0, x of t plus h minus x of t over h. Taking the t plus h, plugging it into the function, then subtracting off the function, dividing by h. This is the thing I need to simplify. Now, it's a compound fraction, one fraction inside of another, and those are never fun. So let's rewrite the division by h as a multiplication by 1 over h. I think now it's a little more clear what's really in a denominator. So I need to cancel that 1 over h at the start of this expression. And I'm going to do that by getting a common denominator for the 1 over t plus h and the 1 over t. Essentially, here I'm cross-multiplying. So that bracket becomes t minus the quantity t plus h over t plus h times t. Distributing the negative sign and canceling the t's, I just get a negative h in the numerator. And now the h's cancel. There's no longer that factor of h in the denominator, so it's a good time to try plugging in. The limit law is going to apply. I can just do direct substitution. And I get the derivative now, dx dt, is negative 1 over t squared. So my second goal in this problem was to find the particle's instantaneous velocity at t equals 2. So I can literally just plug t equals 2 into this formula to get negative 1/4. Notice the notation here, by the way. dx dt, the derivative of x with respect to t, and then I have that vertical line with the subscript t equals 2 to indicate that I'm supposed to be evaluating that derivative at t equals 2. That notation is pretty common. We say that a function is differentiable at a value x equals c if the derivative is defined there. In other words, if this limit exists. Now, there are really only a few things that can go wrong, a few different ways that the derivative can fail to exist. Let's run through them really quickly. We already mentioned that the derivative will fail to exist if the function isn't defined at the value x equals c. I can't plug c into the left-hand side of this equation if I can't plug it into the right-hand side. The second thing that could go wrong is that the function f could have a jump at x equals c. And in that case, one of the one-sided limits of this expression is going to fail to exist. Closely related, the left and right limits of this expression, f of x plus h minus f of x over h, could be different. They could both exist, but they could be different. Fourth, this limit could be infinite, so the expression for f prime of x would have a vertical asymptote. And finally, as h goes to 0, that expression could just oscillate back and forth without ever really settling down. Let's wrap up this video by seeing a picture of each of these situations. It's good to be able to look at a graph and be able to tell where a derivative might not exist. First of all, the situation where we have a hole in the graph. Here at x equals 2, we have a value that's not in the domain of f, so it can't be in the domain of f prime. Secondly, Here's a function where we have a jump discontinuity at x equals 2. In the definition of the derivative, the left-sided limit will not exist. Next, a function that has a corner. In the definition of the derivative, the left and right limits will not agree. Intuitively, we're seeing that the slope of the line tangent to this graph on the left of x equals 2 and the right of x equals 2 are not going to be the same. There's going to be a jump in the slope of that tangent line. The derivative isn't going to be defined at x equals 2. Next, a situation where the graph has a vertical tangent, in this case at x equals 3. By the way, notice that this function is actually a function. Each x value has one and only one y value. The tangent at x equals 3 is vertical, but only for an instant. On either side of x equals 3, it becomes non-vertical again. If we were to compute the limit definition of the derivative, we would see that we have a 0 in the denominator, but not in the numerator. Finally, and probably least important at the level of Calculus 1, is the situation where the tangent line has a slope that oscillates wildly back and forth as h goes to 0. Here's a graph of a situation where that's happening. We can see the slope of the tangent line is going to be changing from positive to negative back and forth as we get closer and closer to x equals 0. So if I were to compute that limit definition of the derivative as h goes to 0, the expression for that slope of the tangent line will not settle down to any one specific value.